Listo, listo, Rafa. Ahí se está transmitiendo. 1, 1. Ah. Okay. Very good.
Shall we start? Okay, so at the end of the previous lecture I was getting to this point where I was showing you some results of what we can measure with weak lensing about the mass distribution around galaxies. So what we had was here from the Sloan survey, which is a very large imaging survey, by no means the best in terms of image quality, but a very, very famous, very large one. And what we can see here is that you can trace all the way out to a megaparsec or more the effect of weak lensing due to the mass distribution around galaxies. So this is really the best way to study dark halos of galaxies out to many hundreds of kiloparsecs, much further than you can study with satellites or with any other way, really. And as I also explained, this is the mass, this is all the mass that you have around the average galaxy, so that includes not only the halo of the galaxy itself, but also all the satellites and all the clustering of galaxies associated with massive galaxies that we're choosing to stack on. Now you can try to go further. You can try to go further and also look not just at the monopole, if you like, the circularly symmetric distribution of matter, but you can also look at the shape of the halo. You can try to see whether, on average, galaxies are sitting in round mass distributions or in elongated, flattened distributions. If the lenses are flattened, then you get this kind of a pattern. Then for a round lens, you have a symmetric tangential distortion. You have this tendency to make all the galaxies a little bit squeezed in the radial direction. If you make the galaxy elongated, the lens, then you see that the symmetry is broken, and you get a different, in fact, you get a stronger squeezing here along the major axis of the lens, and a weaker squeezing here on the minor axis of the lens. So this is a modification of what's already a very subtle effect in the data. Right? If this is difficult to measure, this change is going to be even more difficult to measure. But nonetheless, if you have a big enough data set and good enough data, you can try to do this. So the idea is to look for this pattern here by stacking the galaxies not just by position, but also by orientation. So you stack all the galaxies in such a way that you line up all their major axes and try to look for this modulation, this slight asymmetry in the tangential shear pattern. So then the shear pattern depends not only on distance from the lens, but also on angle with respect to the major axis, like we have here. Right? So for every galaxy, you don't average just the tangential shear, but you also look for something that goes like the cosine of twice the angle with respect to the position angle of the lens. That's that angle there. And so this is something that would be very interesting to do, because you're able to measure 300, 400 kiloparsecs from a galaxy. You're able to measure whether the mass that sits around it is round or is flattened. And that, for example, if you have a theory for dark matter which involves not some particle of matter but some modification of the law of gravity, you probably have a very strong prediction for what that shape should be. And so this is a very nice way in which you can try to test this with real measurements. Now it's too early still to measure these things. We're trying very hard. But we really will need the power of one of the big modern surveys like the KID survey that I talked about last night to be able to measure a convincing signal. So we've tried to do this. At the moment, we don't have anything to report yet. So this is a summary of the first lecture that I gave before the break, and I'm finishing now, which is really the range of applications that we can have for this weak lensing phenomenon. It allows you to study mass distributions much further at much larger radii than just the inner parts where you have all the strong lensing phenomenology. So you can measure the distortions of galaxies and look for correlations in them, which gives you the cosmic shear, the statistics of the large-scale distribution of matter on cosmological scales. So this gives you the power spectrum of matter, basically, which you can compare to simulations. That requires very large areas of the sky that you're homogeneously mapping and analyzing. You can also do the stacking analysis that I showed you, which is galaxy-galaxy lensing. There the idea is that you're weighing the galaxies. You're trying to see how strong the effect that the average galaxy produces is. And you can, as I just showed you, measure this out to many hundreds of kiloparsecs. So a very wide reach for this weak lensing. And you're talking about shears, about distortions of less than 1%. So very, very subtle effects that you can only get to by very careful analysis and averaging huge statistical samples of galaxies. And then the third thing you can do is you can make actual maps of the mass distribution. You can take clusters where there is a lot of distortion, where there's a lot of signal in a small part of the sky, and you can try to invert, using these Fourier techniques that I described, you can try to invert the map of the distortions that you measure into a map of the projected mass distribution of kappa, and give you a very detailed picture of the lensing mass distributions. And for that you need really very good data, very high signal to noise, because otherwise you're just dominated by noise rather than the signal in the data. Okay, so what I would like to do for this final lecture is to show you some examples, in particular of this cluster mass reconstruction and how it works, and also give you a feel for the limitations that you have to work with when you're doing this. So it's here. So this is more of the applications of weak lensing rather than the theory. And so I'll talk a little bit about cluster masses and mass maps, and then also in more detail about what you can do with this cosmic shear, the statistical large-scale structure measurement of the distortions. But first, let's go to clusters. So remember what we can measure. We have the tangential shear, which is the mass contrast, the average surface density within an area minus the surface density at that radius. And so once you can measure this, that gives you all the information you need to construct the radial mass profile of the cluster. You can basically integrate this up. The tangential shear is this combination of the kappas, which is this integral here. Right? The average kappa is the integral over a disk of kappa divided by the area of the disk. And that you can rewrite in terms of the dimensionless mass included in the disk. This is the average kappa. And that gives you a relation about this function m. M is the mass enclosed as you make ever larger circles of radius theta. This m function is the cumulative mass distribution within a certain radius. And as I said before, this works exactly for axisymmetric lenses. It also works very well for non-axisymmetric lenses, if you simply average around the circles your tangential shears. So if you have such a measurement, supposing that you've measured this gamma t at a particular radius, in the way I described before, that means you have the derivative of this enclosed mass function, right? So you can integrate this up, and the way to integrate this is to integrate out to infinity, because out to infinity you can get to the total enclosed mass, and you know that the shear goes to 0 at large radii, so you know the integration limits. So when you integrate this relation out to infinity, you end up basically with an integral over the shear beyond a certain radius. Now it's always nice to write down integrals to infinity. Of course, in practice, when you're doing this with data, you cannot do this. You don't have infinite information. And so in fact, what happens is that you have to truncate this somewhere at the edge of your data, or at the edge of where you believe your measurements are accurate. And so this is going to give you a lower limit. You can measure some of the mass, but you may miss some of the mass at the largest radius when you do this integral. So it's very easy from a shear profile to get a lower limit for the amount of mass within a certain radius. And that's already very important, because that tells you already the minimum amount of dark matter, for example, that you have sitting in a cluster or around a galaxy for which you've measured the shear very well. Now if you want to do this in clusters of galaxies which are very massive, which are the nicest ones to work with because the signal is the strongest there, in those cases, when you get into the inner regions, you have to worry a little bit about the strong lensing effects. So the weak lensing effects are kind of approximate. You don't really measure the shear exactly. You measure a combination of the shear and kappa, which is called the distortion. And this is, again, related to this mass sheet degeneracy that tells us that we cannot quite measure everything uniquely from lensing. But that's a detail. Usually we stay far enough away from the clusters that kappa is so small that this difference between G and gamma is irrelevant. But when you go close into the cluster, you have to think about that effect. So this shows you how from a tangential measurement, a measurement of the tangential shear, you can get a good constraint on the mass distribution in a cluster. It's a very important way to try to settle one of the big conundrums even in cluster studies, even today still, and that is to ask what happens when you get to the center of a cluster. What does the mass distribution look like? There are basically two possibilities. You can have what's called as a core, which is a smooth mass distribution. That's a mass distribution where if you plot the density as a function of radius, you end up with a finite value which then starts to drop off, but there's a kind of core radius over which the density doesn't change very much. So this is what's called a core. Or you can have a cusp. And a cusp is a case where the density, at least as far as you can see, with your limited resolution, is singular. So the density formally here goes to infinity. So at small radii, it basically follows not something nice and regular, but it goes like a power law, which gets larger and larger and larger as you get closer in. And cold dark matter simulations predict that you get these really very high densities in the center, because the cold dark matter basically collapses and collapses and collapses and doesn't have any pressure. And so lensing is one way to try to measure the difference between these two things. And it's really quite an important physical question to try to understand which of these two it is, because this shows dissipationless collapse, and this shows the effect of baryons and hot gas and all kinds of other things. Now the shear measures the average surface density minus the surface density at the radius. So if you have a core and you get quite far in, then you see that kappa and the average kappa inside that radius is basically the same. So this shear is going to go to 0 as you go close to the middle in the case of a chord profile. For a chord profile, kappa bar minus kappa goes to 0. As r goes to 0. Whereas if you have a power law, for example, then that doesn't happen. For a power law, this ratio remains a power law, or this difference remains a power law. So if you make a mass map, or you make a mass of the shear of a galaxy cluster, and you see that the shears towards the center go down to 0, then you know that you have a chord density profile. If you see the shears keep on getting bigger and bigger and bigger closer to the center, then you're in the situation of a cusp. So this is a very nice theory. In practice, it turns out to be very difficult to make this kind of measurement, unfortunately, and I'll show you why in a second. But so this is one of the main motivations for trying to measure mass maps of clusters very accurately. So let me talk about one beautiful example. This is really the best lensing cluster in the sky. This is the best cluster we know, the most beautiful lens that we have. It's an old, well-known cluster, Abel 1689. It's got a huge critical density. It's really got a very large Einstein radius, more than an arc-minute in radius. So there's a very large area of the sky which is affected by strong lensing effects, and a much larger area surrounding it where you can measure all these weak lensing effects very well. Question?
Yes, question. Okay, almost any Abel cluster is beautiful. Yes. So could you tell us about this Abel survey or Abel catalog? What is the purpose of the catalog? And
actually, I'm not sure exactly how this was made. I think it's a very old, basically optically selected cluster sample, where it's very difficult to reproduce exactly how it was made, because it was done by people and not in an objective computer-generated way, as far as I know. But it's simply a collection of the most beautiful clusters that were seen at some point. Later, there have been many other clusters added by looking for X-ray detections or radio or whatever. But this is really the collection of the oldest and therefore the most easy to see and therefore the biggest, most spectacular clusters that we have.
As far as I recall, it's mainly a single man's effort.
Yes, exactly.
And so that's why it's badly documented, because he was not particularly interested in doing much more than just getting this catalog and having it.
It's just a long list of clusters that he found, but not all the clusters above a certain brightness or in a certain part of the sky. It's simply...
So just one man?
Yeah.
Oh my God.
Mr. Abel. He probably had some students.
Usually you get the best consistent results if you need man-made effort to select, and you want that selection to be relatively uniform over the whole sky. Then there's only one way of having that. Let's have one man do it.
Yeah, that's true.
But it doesn't include just compact clusters.
No.
It also includes...
Nice clusters.
Yeah. So in fact, most of the clusters in the Abel catalog are at quite low redshift, because those are the easiest to find in the old photographic surveys that he was working with. And there's a number of clusters which are so spectacular that you can even see these in these data. They're at higher redshift, so they're much more massive because they're fainter or they're further away, but yet you can see them on photographic plates. And the further you go, the stronger, the more efficient lensing becomes, and so that's why the higher redshift Abell clusters are the ones where we have these spectacular lensing phenomena. So this is really one of the nicest and best studied clusters in the sky that we have. Not only is it, and it really has also a very rich phenomenology of strong lensing. So there are many constraints on the central mass distribution from strong lensing. There's more than 40 background galaxies that are multiply imaged. So each of those gives you a constraint on the lens model. So there's a tremendous amount of information there. This is just a subset of them. You see lots of these things. This is 32.1 and 32.2. This is source number 32, which is imaged twice. And you see this count here goes up to 40. So there's lots of background galaxies, multiply imaged, which gives you a very good, very strong, strongly constrained, strong lensing model for this cluster. And if you have time, just go to Wikipedia or wherever and look for a beautiful image of this cluster, and you can have a wonderful afternoon. It's really nice. There's also some strong lenses within this cluster. So there are some galaxies in this cluster which act as their own strong lens, on top of the fact that they're sitting in this lensing environment of the parent cluster. In fact, I think there are 5 in total, and they tend to be sitting around the outside of the cluster. So the cluster kind of helps to increase the lensing efficiency and makes these galaxy lenses act like strong lenses. And they're a little bit like the many strong lenses I showed you from the SLACS project, except these are sitting in a cluster as well. So if you subtract the galaxy off, like we did before, then in this case, for example, you can see 4 little dots, which are some background source being lensed by this galaxy and the cluster. Here there's a beautiful arc sitting around this lens with a counter image. Here another arc with a few counter images. This is, as I say, this is all part of this very rich part of the sky as far as lensing is concerned. Now to analyze such a cluster, supposing I give you a big image of this cluster and I ask you, do what you can, understand the lens as much as possible. Then the first thing you have to do is separate out what is in the cluster and what is behind the cluster. Because the galaxies in the cluster are part of the lens, but they're not being lensed themselves. The galaxies in front of the cluster do nothing. They don't get lensed and they're not part of the cluster. And the galaxies behind are the ones that are not in the cluster. They're not in the lens, but they're feeling the effect of the lens. And this is already quite tricky. In principle, the only way to do this right is to measure redshift for every single galaxy in the image here. Here. For every single galaxy in this image, and maybe over a much larger part of the sky, you would have to measure every single redshift, and that tells you which of the galaxies have the redshift of the cluster, which of the galaxies are behind, and which of the galaxies are in front. Now that's in practice impossible, and so you have to use other tricks. And for example, one thing you can do is you can plot a color magnitude diagram, so a brightness versus color of the galaxies, and you see always in massive clusters these very nice what are called red sequences. These are galaxies which are quite red and which all follow a very nice little sequence. And all those galaxies are the heavy elliptical galaxies that are sitting in the galaxy cluster itself. All those belong to the cluster itself. If you had such galaxies as different redshift, the color would change and they would fall off the sequence. So this is one of the best way of picking out at least the massive galaxies in a cluster. And that's good because those are the ones that are the most important components of your lens. So that's typically where you start. You try to find the most massive galaxies in the cluster. And you see this is not an exact science. There's going to be some, you have to decide where to draw exactly this line. If you move this line up or down a little bit, a few galaxies will fall in or out of the cluster. So you have to live with uncertainties. And as the fainter galaxies goes, it gets much more complicated. Faint galaxies, it's very hard to tell from color diagrams like this whether they are in the cluster or in front of it or behind it. So you have to do it statistically. And in this study by Limousin et al., this is how they did their cluster selection with which to make the lens model. That's the basis of their whole analysis.
And what is the astrophysical reason for having this clustering in this mass color relation? It's to do with how star formation happens in more massive and less massive galaxies. So if you take at the same time you form a bunch of galaxies, the more massive ones will retain more of their gas, and so they will have a slightly different kind of population. It's probably a metallicity effect than the lighter galaxies. But the point is it's like a one parameter family, and the one parameter is the mass of the halo in which these galaxies form.
But if you knew the exact answer to this, you would be very famous. It's one of the puzzles of galaxy formation. And so using all these massive galaxies that they found, they construct a strong lensing model. And the strong lensing model includes an overall halo for the cluster, which you don't know the parameters of, so that has a few free parameters that you fix by making the strong lensing work. And on top of that, you put a halo or some mass concentration around each of these galaxies. And you put more mass around the bright galaxies and less mass around the faint galaxies. And again, that relationship is something you can try to test with your strong lensing model. And so this, based on 40 multiply imaged background sources, most of which have redshift so that you can really do the lensing calibration very well. And this is the critical curve of this model for some redshift. I don't know what redshift of the source, but you see very complicated substructure. This is one of these examples of a smooth profile in which you add lots of substructure, and so you end up making lots of extra peaks in the Fermat potential. Remember the movies I showed you yesterday? All these extra bumps give rise to kinks in the critical curve and give rise to extra sets of images from background sources. And so this model, it looks very complicated, but it's actually it's put together in a very rational way. It's simply putting mass where you see the galaxies, and on top of that adding a smooth distribution to represent the dark matter that's in this cluster. So this is a way to learn a lot about how mass is distributed in galaxy clusters. So just for fun, these are the caustics and the critical lines of this model that I just showed you. So here are the critical lines again on the right, and these are the caustics. So remember the kind of simple caustics that we've been playing with before. Even the binary cases, which look complicated, are nothing compared to something like this. And this is because there's all this structure in the lensing potential. So there's no way you can work with this analytically. You really have to do this in computer simulations. It's quite a heroic effort to construct something like this. And so by now, these people are able to do this for many of the lensing clusters that we have. There's many models like this for different clusters. And these are all very complicated pieces of optics, if you like, that are hanging in the sky with which we can study the universe much, much further behind these clusters.
My daughter is very good at drawing this kind of caustics. My daughter.
Your daughter?
Yes.
Probably she would draw it on the screen so it would stay forever too. Yes. Okay, so let's see what we can do analyzing this model. So this is what we get just from the strong lensing, just from the model that explains the positions of these multiply imaged sources quite close in within the Einstein radius, more or less. And so that gives you a range of radius out to a few hundred kiloparsecs in this massive cluster, where you get information about the mass distribution. And what's plotted here is the projected mass enclosed within a certain radius. So as you make a larger and larger radius, you ask how much mass is there within a circle larger and larger and larger on the sky. So this curve is always going to increase because you're always taking more and more and more of the cluster in your aperture. But of course, the slope of it can change depending on the mass profile of the cluster. So the gray band here is what you find putting in the uncertainties from the strong lensing model. You see it's really very small. So the strong lensing really is very well able to constrain the enclosed mass. And there's a few other earlier analyses of the same cluster which show pretty much the same results. So strong lensing really is a very robust way of constraining masses. The dotted line here is a different, I hope you can see it, it's a different analysis, which is nothing to do with lensing. This is to do with X-rays. So this is where you take a picture of the cluster in X-rays. You see the distribution of the very hot gas that sits everywhere in the cluster. You measure the temperature of the hot gas, and you ask how much gravity do you need to keep this hot gas inside the cluster and stop it from either collapsing or flying out. It's basically hydrostatic equilibrium, like you could do for the atmosphere of the Earth, but now for the gas that's sitting in this cluster. And you see that things agree within about a factor of 2, which in astronomy is usually not bad. But you can also see that with lensing, we're getting to a regime where you can really do things much more precisely, if you do things right. And on the right is a different representation of this mass profile, which we can skip. On the right is a fraction of the mass which is in the galaxies. So you can do the same thing. You can put a bigger and bigger circle on the sky and just count how much light is in the galaxies in the cluster. And you can calculate this mass to light ratio, and that's effectively what this is. And you see that as you go to larger and larger radius, the fraction of mass that's in the galaxies is getting smaller and smaller and smaller. In other words, more and more dark matter at large radii compared to in the center. Now let's add the weak lensing. Remember, the strong lensing got us out to a few, let's say 200 kiloparsecs. Now with the weak lensing, we can go out here to a megaparsec. And that's simply by adding the regions outside the Einstein radius where you do not get multiple imaging, but you do get this systematic distortion, this squeezing due to the outer regions of the lens, the weak lensing properties. Now, and here things get very tricky because again you have to make sure you're using the right galaxies to make this measurement. Again, if you have the cluster, let's try to draw this. You have your cluster which consists of lots of massive galaxies. Those are the ones, I don't have a red pen, but those are the red galaxies that you choose in the sequence. And then on top of that in the sky you have lots of other galaxies, many of which are behind the cluster, many of which are in front. And you'll find those everywhere. Some will be right behind the cluster, some will be far away. But this cluster is not something that has a sharp edge, so the cluster galaxies also will be found at larger radii. And so the problem is if I take a small part of the sky and I try to measure what's the average tangential distortion in this part of the sky, I have to make sure that I'm only averaging over galaxies which are sitting behind the cluster. If I take galaxies which are in the cluster, those galaxies will not have a specific alignment because they don't feel the lensing. And so that would dilute the signal. That would mean that I underestimate the strength of the lensing signal because I'm including galaxies which are not being lensed. And so this selection of what is in the cluster, what is behind the cluster is again very important in order to get a good measurement of the galaxy cluster mass profile. And the further in you go, the more important this gets, because the further in you go, the more galaxy clusters you have, the more cluster galaxies you have, and so the stronger this contamination is going to be. But the further in you go is also the place where you want to ask this question. And so that's why this is actually a very delicate experiment to do in real life, because if you want to look into the core of the cluster to see what the shape of the mass profile is, that's kind of by definition where the galaxies of the cluster are also, and that's where you have this contamination problem. And so this is something which traditionally has given very diverse answers because different people have different ways of doing this cluster galaxy selection or cluster galaxy elimination. And in the end, the only way to do this properly is going to be to measure lots of redshifts of galaxies and actually galaxy go through and figure out which galaxies are in the cluster and which ones are not. So here the claim is that the typical NFW profile which you expect from cold dark matter halo collapse is a pretty good answer, a pretty good fit to the data. The different symbols here, the red and the blue, show you what happens if you make different selections for what is a cluster galaxy and what is a background galaxy. So it shows that you can get factors of 3 or 4 difference at small radii because of this. At large radii you still have the problem, but it gets less important because at large radii, in any case, the background galaxies dominate the cluster because the cluster gets more and more diffuse. But so it's very important to try to get this because this is really one of the mass profile of clusters is one of the strongest predictions of simulations of how galaxies form and how matter clusters in the cosmological model. And so being able to test this with real measurements that you believe is a very important way to make sure we're on the right track. And so that's why there's a lot of work going into this. But I think the final word has not yet been said on this. Here is a way of constructing the mass map of the same cluster. So this is, now it's a black and white, it's the same part of the sky more or less. And here on the left is the shear field. So here what you do is you take small pieces of the sky. In each of those pieces of the sky, you measure the average ellipticity of the galaxies by calculating these E1, E2s for everything, making that cloud of points and seeing where the center is. And in fact, here what you see is that as you go towards the center, the shear seems to go down. The largest shear happens in a ring a little bit further out, so that would indicate that there's a core in this distribution rather than a cusp. Once you have this shear map, right, everywhere on this map you have a value for the shear, you can do this inversion and make a mass map. And the mass map is shown here in contours. I'm not sure you can see it very well. These contours are contours that enclose constant surface density of the cluster. So that's really a reconstruction, turning these shears into a kappa, into a surface density mass map. And you see it's not perfectly round. There's structure in there, and some of that structure is real. Some of it is noise, but it's, in principle, you can make these measurements as good as you can, and then you can really ask for each of these features. Maybe there's a separate clump here. This center of the cluster seems to be double. You can do simulations and ask whether that's real or whether that's probably noise. Most of the structure that you see here, in fact, is real, we think. And you can do this with many clusters, and it has been done with many clusters, both using imaging from the ground, but mostly using images from Space Telescope, where you can see the shapes of galaxies more accurately, and also where you can see more galaxies, so you can improve the statistical accuracy of your mass map even more. So this is a cluster with a telephone number up there. It doesn't matter which one it is, but this is a mosaic of lots of images of Space Telescope all stuck together. Each of the little lines here that you see is a measurement of the shear in that small part. It's been smoothed a little bit to be able to give a good mass reconstruction. And so here on the right you get the corresponding smoothed distribution of the mass in the galaxy. And if you look at the distribution of galaxies in this cluster, in fact you also see that it's elongated in this direction. So typically you do find that the mass follows the shape of the distribution of the galaxies in a cluster reasonably well. You also see here what I was talking about before, the boundary effects. When you get to the edge of this map, you begin to see funny features, and many of these features are because you actually lack information at the edge. So you should never believe the edge of a mass reconstruction. You should always concentrate on the central parts, where you have complete information. This was done by a PhD student of mine a while ago. Here's another cluster that he did. This was at a much higher redshift. This cluster is at redshift 0.8, so it was one of the highest redshift clusters where we can play this game. Remember, you need galaxies behind the cluster, so you need galaxies at redshift even higher, where you can still measure the shapes. So these galaxies are very faint and very small, so you need really good Space Telescope imaging to be able to even measure shapes and get a shear field and come out with a believable mass.
How far in megaparsecs is this cluster? More or less.
Redshift of 0.8 is going to be gigaparsecs.
How much? How many?
Yeah,
do you remember? Is 1, 2?
I can work it out, but not live. I'll switch off the camera and then I will. This cluster, I mean, this is roughly halfway back to half the age of the universe, give or take. So, far. And so what's interesting is here you really see that this is not a round mass distribution at all. And you can try to do statistical tests and you find that round models simply do not capture all the structure that we find in this map. And what's even more interesting is if you look at the distribution of the galaxies, which is plotted underneath, you see there's a clump here, there's a big clump here in the middle, and there's another clump here. And this is exactly where the mass contours that you see here are the highest. So this really shows that this is a system, a cluster which is still very young and still forming. You have 3 big clumps which are still merging together for the first time. And what you're able to see in this weak lensing map is that the mass is also still associated with these subclusters.
So my point is, how likely is that you can see these far clusters inside all this structure between them and us? It's a miracle. It's something like a miracle.
So finding these high redshift clusters is a whole art in itself. I think this is a catalog this cluster emits in X-rays. And so one of the ways to find clusters is to look for X-ray emission. You see this hot gas. And then you can look at those positions in the sky and try to estimate the distance from the colors of the galaxies that you see in there. But this is actually one of the most distant, very massive clusters that we know. And it was found in this way because it's quite bright in X-rays first. But yes, you're right. If you look at this picture, most of the galaxies are going to be not in the cluster, but are going to be in front of it. There's now another way in which you can find clusters, which is through the Sunyaev-Zeldovich effect against the microwave background. Again, the hot gas in the cluster causes a change in the spectrum of the microwave background, and you can see these spots. And in fact, there are now catalogs with many hundreds of such clusters, many of which will be at high redshift. In fact, you're equally sensitive to those clusters at all redshift, so that's very interesting. But so the point I was trying to make here is that you should believe these mass maps, because what you get is very sensible in the sense that the mass seems to concentrate around the clumps of galaxies in what's clearly a cluster that's still merging and pulling together. So this just shows that this is really a very important tool, and you can, for example, measure the mass of each of the separate clumps and predict how massive this cluster is going to be when it grows up, so to speak, when it's one big relaxed cluster, and relate that to the present day universe. Here's another system which another student of mine is working on, Marijn Smit. This is a system, this is at lower redshift, but this is consisting of about 5 or 6 subclumps. So this is a cluster where you have 1, 2, 3, 4, 5 groups of galaxies, all at the same redshift, clearly all associated with each other, that will presumably be merging, falling into each other at the moment. And you can play the same game. You can try to measure the mass of each of these clumps and figure out over what time, what the future of this cluster is going to be. On the right here, you have the distribution of galaxies. So this is simply the light of the galaxy smoothed to the same resolution as we have here. And you see the same clumps in the light distribution as you see in the mass distribution.
Teacher.
Yeah.
Hola. Profe, ¿con qué profundidad se toman esas imágenes? ¿Un centro de masa o sea, qué tan extenso es el campo con que se observa eso?
So to be able to make these mass maps, you need to measure the shapes of lots of background galaxies. So you really need very deep space telescope images, which go down out where you see galaxies out to redshift 1. Was that the question?
Profe, por profundidad digo que hay una distribución de masa, ¿cierto? Entonces tengo mucha acá y un final en la parte de atrás. Esa imagen es plana, sí. Pero esas imágenes, ¿dónde están centradas? ¿En la parte más cercana, en un centro, o cómo escojo yo el lugar donde trazo esas curvas?
We really don't know. All you can measure with lensing is the projection of the full distribution of mass. And whether it's thick or thin is hard to say. You cannot tell from the lensing because the light flies past so fast that the bending effect is actually pretty much the same, whether everything is in a single plane or stretched out over quite a large thickness. So we do not get the third dimension on the scale of a cluster. You can tell the difference if there was a cluster here at redshift 0.6 as well as these guys which are at redshift 0.3, you would be able to tell the difference. But not whether this is round or stretched or flattened. The picture in the middle is interesting. Remember I told you that when you do these mass reconstructions, you go to Fourier space and you come out with a complex map of the surface mass density, where the real part is really the surface mass density that you know and love, and the imaginary part is spurious, should be 0 if everything is perfect, and is due to noise when it's not. Well, this here is the imaginary part of this. So this is the real part, and this is the imaginary part of the same reconstruction. And so you can plot it on the same scale, and you can see that indeed the mass concentrations that we detect here are at a much higher level than anything you see in this map, which is mostly noise. So this map sets the level of noise. This tells you the kind of things you should not believe necessarily in this map, but it also tells you that things like this are really very well detected structures in the lensing map. And those are the ones which happen to coincide exactly with where we see the clusters in the galaxy distribution. So it all hangs together very nicely.
But why? Why the imaginary part is the noise?
You should have been at the previous lecture.
Okay, thanks.
So very quickly, the point is that you can take the shear that you measure, and there's an inversion in Fourier space which gives you kappa. And that inversion gives you kappa, which is then going to be a complex number. And the complex number should be real if your data were really all due to lensing. If there's some other aspects, either noise or mistakes in your measurement or contamination from cluster members or something like this, then you might get an imaginary part. And so this imaginary part is kind of a sanity check or a consistency check to make sure that it's a way of estimating the level of noise in your map. But if you look at the slides of the lecture you missed, you'll find it.
Do it.
Right. So all of this is basically me giving propaganda to you that weak lensing masses are things you can measure, that you can make these maps, that they're very useful and that you should believe them. Right. So the bullet cluster we talked about before already. This is this collision of two clusters which tore apart two clusters and left the gas sitting in the middle, whereas the galaxies flew straight through. And this is one of the most important physics experiments that we've been able to do with weak lensing, because it shows that the dark matter is collisionless and associated with the galaxies rather than with the gas. Okay, so much for mass maps. Any questions on this before I move on to cosmic shear?
Bullet cluster. Could you go back to the bullet cluster?
You should be in the previous lecture.
So, blue is the distribution of dark matter as measured with this method. But my question is how they measure with such detail the distribution of gas.
It's an X-ray image.
It's an X-ray image, but
yeah.
X-ray is not too. It doesn't have this kind of resolution. Okay, I'm just asking.
No, I guess this is a picture with Chandra, which has a very. I mean, this is quite a large part of the sky. This is several arc minutes on the sky.
Oh.
So this is a big thing.
Is that large? Mm-hmm. So arc minutes. Okay.
So I wish we were able to make weak lensing maps which had the same fine structure as X-ray. We're not there yet by any means. Okay, so then let's talk about the other big application for cosmology, which is what we call cosmic shear. Not looking for lensing patterns around galaxies or clusters that we see, but simply looking at the statistics of the fluctuations in the shear that we see on the sky. And so this is lensing by the large-scale structure, which is mostly delineated by dark matter, which we cannot actually see. So it's really a direct experiment to try to measure how clustered the mass distribution is. So the way we characterize clustering normally is by the power spectrum of the density. You ask on what scale, on every scale you ask how smooth is the matter. So you imagine taking the universe, smoothing it on a scale of 1 megaparsec, 2 megaparsecs, 10 megaparsecs. And you ask how small or large are the ripples in the density on those scales. That basically tells you the power spectrum, tells you whether there's lots of small scale structure, lots of large scale structure, etc. And this is exactly what we can measure with cosmic shear as well. If you imagine decomposing the distribution of matter into Fourier modes again, so here's one mode, which goes up, down, up, down, up, down, up, down, up, down. In gray you have the distribution of mass. And such a pattern will lens the background galaxies systematically in this kind of a pattern. Wherever there's where the lensing potential has a maximum, you get a stretching this way. Where it has a minimum, you get a stretching that way. Or vice versa. I can never do the signs live, but you can see that you will get the same waving pattern in the shear as you get in the lensing potential, and the lensing potential, of course, is related to the mass density. And so this is something we can measure. We can simply look at all the galaxies in this part of the sky and see if they tend to be aligned this way, then look at all the galaxies here and see if they tend to be aligned this way, etc., etc. And so that is the way to measure the amplitude of one of these Fourier modes. And you can do this again and again and again for Fourier modes with longer wavelengths in different direction and reproduce the full Fourier sky in lensing. So this is something that can be measured, and it's something that we're doing routinely with our large images now. And so the point is, you don't need to know where there's no cluster or no galaxy in front that you're trying to measure the mass of. You're simply trying to measure the amplitude of these modes in general. And so this is important because it's a way to test the cosmological model, which says that all the structure that we see now grew through gravitational instability. So this is one of these huge computer simulations which show how, starting from very smooth conditions, you make all the large-scale structure through gravitational collapse. And so large structures, large clusters, massive filaments, huge empty regions all form through the same process of gravitational collapse. And this is something which we can describe statistically very well, but you really need to do these big computer simulations to get a coherent prediction. Is that a question? And so this is what we can measure with lensing. We can do the statistics on such a simulation, and we can do the statistics on the sky, and we can see if they agree. This has a very well-defined power spectrum, this matter distribution, and we can check in the sky to see if it agrees with what we measure. So cosmic shear really is a very strong cosmology probe, and in fact it's one of the most powerful cosmology probes that we have, provided we can keep control of all these systematic errors that make it very difficult to make these measurements accurately. And in fact, we try to do this by going to 3 dimensions. We try to combine the shear power spectrum with the redshift of the sources, so you can do a kind of tomographic analysis. And I'll show you in a second how that works. But we're trying to measure basically 2 effects. One is how fast structure grows. So we're trying to see redshift slice by redshift slice what this power spectrum is, and then you can see that the structure is growing, that the amplitudes of the fluctuations are getting larger. And the physics of those fluctuations is very simple. It's a competition between the universe that's expanding, that's pulling everything further apart, and the gravity of overdense regions that are attracting all the material around it. And so this competition you can describe mathematically very simply, and it gives you, for any expansion history of the universe, it predicts how fast structure should grow. So this amplitude of the power spectrum as a function of redshift or of look-back time, or however you want to look at this, is also a probe of the expansion history of the universe as a whole. These 2 things are intimately related to each other. The second thing we can do is to do a purely geometrical measurement of cosmology. We can basically use the angles in the optics of a cosmological lens. This works with strong lensing mostly, to try to see what the difference is between the same lens lensing sources at different redshifts. And that again gives you cosmological information because it tells you about the distances involved. This depends on this quantity called the angular diameter distance, which is something you define in curved spacetime and which is different for different cosmologies. So if you can measure this, again, you're probing the cosmological model. And the interesting question you can do is you can ask if these 2 things agree, if the same model is able to explain both of these 2 things. If it isn't, and you're really sure that it isn't, that's actually very interesting, because that means that gravity is doing something different on the scales where large-scale structure is forming from the scales on which the universe as a whole is expanding. So this might point to modifications of gravity, which maybe help us to explain where this dark energy and maybe even the dark matter really fits in our physical theories. So that's kind of the thought behind these very large experiments trying to measure these 2 things. So we're basically looking for these lensing modes on the sky. Again, as I said before, B modes are things which lensing cannot make, so you split the signal into what are known as E modes, which are this tendency to have an alignment around mass concentrations, tangential alignments. And this subject has been alive since about 2000, when the first detections of this phenomenon were found more or less at the same time by a bunch of different teams. So suddenly this effect was discovered and measured very accurately, also with very good agreement. And since then the measurements have just been getting better and better and better. What this shows you is effectively the power spectrum. It shows on different scales on the sky. So from large scales to small scales, it shows you the typical fluctuations from point to point on the sky. So this is effectively the power spectrum. This tells you that on small scales the fluctuations are very large. So if you go look from 1 arc minute to the next, you will get a very large fluctuation in density. But on larger scales, the universe is much smoother. And the lines through there are actually cosmological fits. So these measurements are also not crazy in terms of what they show us. Now I said that you can use lensing to measure distances. So this movie shows how this works. This is a single lens, the same lens, lensing a source further and further and further away. And so what you see is that the further away the source is, the larger the effect on the sky is in terms of where the image is compared to where it would have been without the lens. So even though the lens is the same, the source distance affects the strength of the effect that you see on the sky. This is the DDS over DS factor that we have in the critical density. It's exactly this. It's the difference between alpha here and alpha hat here, if you remember the first lecture. So if we can take a lens and we can look at lots of sources behind it at different redshifts, then we can try to measure this distance to different redshifts, and that's how we do our cosmology. The same lens will affect sources at different redshifts differently, and we can measure this. Okay, so this is one effect. The other effect is the shear tomography that you can do. The shear depends on the distance to the source and the lens. The distortion matrix also does, and you can try to measure this slice by slice and try to see, well, let me show you on the next picture, on the next slide where there's a picture, I think. This is how this shear tomography works. If you imagine splitting up a long line of sight into a mass distribution at one distance and a mass distribution at a second distance. So in fact, of course, we have a full three-dimensional distribution, but let's consider two different mass sheets, two different lensing planes. And supposing that you measure the lensing of galaxies here at this distance and the lensing of galaxies here. Then the galaxies that are sitting here, their light comes to us only through mass sheet number 1. So these galaxies show the lensing only from this distribution. So analyzing these galaxies tells us the mass distribution here. Now let's make a lensing map or a mass map of the galaxies here. These galaxies we see through mass sheets 2 and 1. And so the lensing map that we see here contains information from both of these. This we already know because we've analyzed this map, so we can subtract this off in some way, and that's a way to tell us just what the mass distribution here is. And so this way you can kind of peel off, redshift by redshift, the three-dimensional distribution and come up with something about the growth of fluctuations from here to here to here over the whole redshift range. So this is just like tomography in a scanner, where you have lots of projections in different directions and you turn it into a full three-dimensional picture. Yes, and all the rest are details about how you would do this mathematically, which on a Friday afternoon, quite frankly, we're not going to go through. All right, the point is that it works. So this is an application of this that a postdoc of mine did on fantastic imaging from the COSMOS project. So COSMOS was a space telescope project that measured a very large part of the sky for space telescope, 1.5 square degrees on the sky, with this phenomenally sharp imaging that space telescope can do. It's one of the largest projects that Space Telescope has done. And it's also very deep, which means you see galaxies to very large redshifts, which means you have a lot of these redshift bins with which you can do the tomography. And so what's shown here is actually 6 different redshift bins, and you see the relation between them. You see the cross correlation between them, which tells you how much of the mass is in front of sheet 1, in front of sheet 2, in front of sheet 3, etc. So the different colors, again, this is a very complicated diagram, but the different colors show different cross correlations between the lensing maps of sources at different redshifts, and that tells you how much of the mass is in front of the first one, how much of the mass is behind it. And the different curves, which have the same, which are supposed to go through the points of the same color, are a model for the standard cosmological model that shows that the amplitudes of these cross correlations that we find are pretty much right. So again, yes. So there are actually more. I'm not plotting all of them because there's also cross correlations between 3 and 4 and 3 and 5 and so on. Yes, it's early days. This is only in quotes 1.5 square degrees. This is why we're trying to launch Euclid, which is going to do this over 15,000 square degrees, and then these error bars will go way down. Okay, so this was the Cosmos field, and when we analyzed this, we actually, just from the lensing alone, we were able to show that you try to see, do simulations with lots of different cosmologies to see whether they are able to predict the level of signal that we see. It is very noisy, as Rudolf said, which means you get a very large spread, but nonetheless, almost all the models that are able statistically to agree with the data that we found are all models in which the universe is accelerating rather than decelerating. So this was completely without supernovae, without measuring redshifts, without measuring magnitudes, purely based on lensing. We were able to show that you need an accelerating model, an accelerating expansion to explain the data, to do this tomography.
And why didn't you win the Nobel Prize?
Sorry?
Why didn't you win the Nobel Prize?
Why did we not win the Nobel Prize? Well, first of all, there's a 10% chance that we're wrong. Right? This is the full probability distribution. Secondly, this was after the supernovae had already told us that there was acceleration. Without that, maybe we would have looked harder to see if we didn't believe the result.
Yeah.
But I think this is a very important proof of principle that when you have a space telescope quality data set over a much larger part of the sky, then this distribution is going to go way down, and you can really measure, you can really do cosmology and do these tests of gravity, for example, using this tomographic technique. So again, these are proofs of principle, early day demonstrations that it's worth to put a lot more effort into this. That's how we see this. Okay.
What about non-homogeneous models? Can you test a non-homogeneous model with a given
I don't know what you mean exactly by non-homogeneous, but here, of course, these models are non-homogeneous because we are seeing lensing.
Okay, I mean at the largest scale. No, it's.
You mean like the?
Yes, a violation of the cosmological principle, like living in a void and things like that. You can.
As soon as they make a prediction, I mean, if you have a metric, you can make a prediction, and you can compare it to the observations. And so we can actually dream and take this even further and think of this as a way of testing our theory of gravity itself. This is what I was telling you before, that the growth of structure has to agree with the expansion history, and we can measure both of them from lensing simultaneously, and of course pull in other data also from different measurements. So the expansion of the universe is governed by the Friedmann equation, which tells you that A dot over A in terms of the density parameters of the various kinds of matter. The matter and the cosmological constant and the curvature all scale in different ways with redshift, and so this is a nice closed system with which you can predict, based on Einstein's equations, how the expansion of the universe should be. The growth of structure, so when you're in the linear regime, when the amplitudes are small, also can be predicted very simply, just as a perturbation of this Friedmann-Robertson-Walker scenario, and you get exactly, you see that the amplitude of a fluctuation again is completely determined once you know the acceleration, the expansion parameter A. So if you know how the universe is expanding, you also know how the structure inside it has to grow. As I explained, both of these things can be probed by lensing, A by doing this geometry thing, and G by measuring the amplitude of the fluctuations at different redshifts. And so combining these two things can tell us whether the GR, you can basically do this consistency relation and check whether GR works or not. And if you really find a consistent inconsistency, you would be in business for trying to find a modification for gravity.
The omega key that remains the curvature of the structure of the large-scale structure of the universe. I remember something about the W map proof, that the measure of this constant was 0. Yes. So we will live in a flat universe. That is possible to measure using lensing, or it's not possible?
In principle, it's also possible, or you can constrain it in some way. I don't think you'll get, it's very difficult to get measurements as accurate as WMAP, certainly from the lensing data that we have now. Right, that's what you saw. WMAP has a very clear prediction for the cosmological constant. We had this very broad range, which was mostly on the acceleration side. So yes, curvature seems to be extremely small. Often you can constrain your results a lot by assuming it's exactly equal to 0 and not considering this parameter at all. In principle, you can put it in. And so, of course, we try to be as general as we can, as long as the data is informative. When the data doesn't tell us anything, then we start making assumptions to get more results.
¿Qué es G en la ecuación de abajo?
G?
G.
G is the amplitude of fluctuations, one of these density perturbation modes. It grows with time through this equation. Very long wavelength modes. So this is something we would love to do, but it's extremely difficult, and it's very difficult because the effects we're looking at are extremely small. So for example, here is the expansion history back to redshift of about 2, where you have a cosmological constant, or you have a slightly different equation of state for the cosmological density parameter, and you see that the effects are really, really tiny. There's a black curve and a red curve which lie basically on top of each other. So this just shows that you need exquisite precision and very good control of systematic errors to be able to make a measurement that you would actually believe. So we really would like to know, can we be sure that the cosmological constant explains all the data, or do we need to do something different to the dark energy? These kind of models are extremely difficult. Both the expansion history and the growth history you see are very, very similar. And lensing is, on paper, extremely powerful, but it also is sensitive to many kind of systematic errors. If you have a tiny mistake in your ellipticities, which is easy to do because, for example, you have to understand how your telescope in the atmosphere blurs the images. If you make a tiny mistake in the ellipticities, you will maybe change by a few % your growth amplitude. And that may be enough to tell you that you have a completely different model. So you have to be really sure that your measurements are correct. The measurements of the redshift need to be very accurate, because otherwise you move points in this direction, and again you will be off the curve and not able to distinguish between the models that you want to distinguish. And so we need both huge statistics and very high fidelity measurements. And this is really where this field is heading. It's becoming very much a precision endeavor to, with a huge number of samples, a huge number of galaxies from a very large sample, try to measure these very accurate things and be able to believe them. And being able to believe them is as much of a problem as just doing the measurements themselves. And so there's a lot of cosmology projects on paper and already on mountains on Earth, and hopefully soon in space, which are going to target exactly this science. So there's very large survey telescopes that want to do these lensing measurements from the ground. This is the KIDS project that I talked about last night that we're involved in Leiden with colleagues around Europe. In the end, we will want to do this from space. And there was various initiatives. There's the European Space Agency is going to launch a satellite Euclid that's going to do exactly this. There's an American project called WFIRST. It used to be called JDAM, which is going to do something very similar. So from space, we have many of the we don't have many of the problems that we have from the ground in terms of image quality. So this is going to be fantastic, but it's going to be another 10 years before we have these data. And there's also different ways of studying cosmology by measuring the large-scale structure of galaxies directly, looking in even more detail at the cosmic background radiation. And in the end, we want to put all of this together and try to get as good a picture of the cosmology and indeed of the laws of physics and gravity on these large scales as we possibly can. And the nice thing about this is that all these surveys basically involve big imaging surveys. So whether you like it or not, you're actually doing astronomy. You're taking pictures of the sky all the time, which lots of other people can use for lots of other things. So this is where weak lensing is going, I think. It's heading for putting constraints on the big questions in cosmology, the dark matter and the dark energy, which are really mysteries in terms of their physics at the moment. We're pretty sure that there is something to explain. So there's really coherent evidence. We know what we would like to try to measure, but we have no idea what the answer is going to be. And so lensing really fits into this endeavor in a very powerful way, and it's already keeping a lot of people very busy. Okay, so I think this is the end of the lecture, so I just have a couple of things to say. This is the end. And I must say, it's been wonderful to see how hard some of you, probably most of you, have been working this whole week, and it's certainly a very stimulating thing as a teacher to see that people are struggling to understand the material that I presented. So many thanks to you.
You have to stop lying us.
Stop lying?
Yes.
Okay, I'm stopping.
Conrado habla español perfectamente, entonces la idea es que te despidas de nosotros en español.
Bueno, es lo que he hecho.
Sí, ese era nuestro pequeño secreto que seguramente conocían. Conrado es honrado.
No,
es el nombre.
No soy español, no soy.
Honrado.
Bueno, me llaman muchas cosas.
Porque en belga, no, francés es Conrad.
Holandés.
En holandés es
Kunrad.
Kunrad.
Entonces hay, bueno.
Pero en inglés, en Inglaterra te dijeron
me llaman Conrad.
Conrad.
Entonces,
a partir de ahora, aquí te vamos a llamar Conrado.
Perfecto.
Bueno, no. Muy bien, con esto entonces concluimos el primer curso del AstroTwinCoLO. No, déjalo encendido por si te pregunto alguna cosa.
No, entonces
okay. Entonces, tienen todos el ejercicio, ya les dijiste.
Sí, for those who were not here before, so the homework of today is also the quiz for this chapter. So it's only one question. If you followed what I explained today, you should be able to do the calculation. Jorge will correct it, and he will be very generous with his points, as always.
As always.
And I think you want this on Monday, no?
Yes.
So on Monday I will no longer be here. But you can hand it in to Jorge, and if there are any problems, then I'm sure Jorge will know how to find me.
Bueno. Pero si han visto el ejercicio es bastante realizable. ¿Cómo dices? Ahí están afuera el ejercicio número 4. Bueno, aquí tengo los exámenes para entregárselos. Es importante que Conrado nos insista en la importancia no del score, del puntaje, sino en la corrección, ¿cierto? Porque de nada pues sirve uno ver que sacó 92 si no va a ver dónde se perdieron esos 8 puntos, ¿cierto? Por favor, revisen bien en qué se equivocaron y traten de corregirlo. Bueno, sobre el curso, entonces, con lo que nos entreguen el próximo lunes, se hace la cuenta de quiénes ganaron el curso, tienen que obtener más de 60 puntos, y se les entrega un certificado de aprobación del curso, ¿correcto? El que quiera tener un certificado de asistencia, así no haya ganado, bueno, you're right, necesitas, no, te vamos a hablar a partir de este minuto en español, además es viernes, vamos a dejar descansar el...
Ya.
Ok, bueno, muy bien, entonces esos son como los detalles de la parte académica. ¿Alguna pregunta sobre eso? ¿Alguna pregunta sobre eso? El promedio sí, es ponderado, es igual valor cada... Dani. Do you understand this?
No. Creo que no quiero saber.
Si no quieres saber. Bueno, muy bien. No, la vuelta es que los 2 cursos se suman y dan la nota final. Listo, ya que hay que ganar los 2 cursos. Bueno, la razón es que tenemos un par de estudiantes aquí que este curso lo tienen matriculado, por eso están aquí.
Claro, si no, no estoy bien.
No, a mí me parece, ahorita hablaba con Conrado y nos sorprendía mucho que hubieran llegado hasta este punto, porque este es un curso muy difícil, muy rápido, en inglés, pero ahorita pensaba ya sentado en que eso es como cuando uno está pequeño, que le aplican las vacunas, vaccinations, ¿ya? Y de uno le aplican las vacunas para que el sistema inmunológico se prepare para lo que viene, esté listo.
Si no se muere el paciente.
Si no se muere el paciente, correcto. Algunos murieron, algunos niños mueren en el camino, otros, bueno. Entonces, es muy importante que hayan llegado hasta este punto, aunque no todo se haya entendido, no todo se va a entender. O sea, yo me acuerdo que en 1998 yo asistí a mi primera conferencia internacional y entendí el 10% de lo que decían, pero no me sentí mal. A la segunda conferencia a la que fui, pues ya me sentía un poquito más confiado. Entonces, esto es un asunto gradual. También se hacen a una idea, porque aquí nosotros tenemos unos cursos de inglés en la universidad, se hacen una idea en realidad de lo que uno debería recibir en un curso de inglés, ¿cierto? Miren que uno se la pasa en el curso de inglés aprendiendo mucha gramática, aprendiendo listening, pero con una persona que pronuncia perfectly, ¿cierto? Que dice perfectly, pero en la vida real uno se enfrenta a personas con distintas entonaciones, etcétera. Entonces uno tiene que hacerse la idea de que no siempre va a entender todo lo que dicen las personas y de que, no sé, hay que educar el oído y el cerebro para eso. Sí. Bueno, Conrado, entonces te queremos ya finalmente para agradecerte. A una cosa también muy importante que quiero decir es que a pesar de todo lo que ustedes crean, Conrado trabajó el doble. Es decir, Conrad, you work the double, maybe the triple. You know, I saw Kuhn working all the time in the slides, in the exercises. So actually, Kuhn, you have done a very, very nice job. I hope that all of you think in Conrad in Kuhn in the future. I was playing with your name because I discovered that most of our students didn't know your name, because I say all the time Kuhn.
Okay.
So it's Kuhn. What is Kuhn? So okay, Conrado. We want to give you a present for your hard work. This is.
Thank you very much.
Okay. Pico. No, Natalia, Nati. Pico, eso incluye un besito de agradecimiento.
En Holanda
Son tres.
Aquí solo decimos.
So, el regalo, como Kun habla español, le hemos dado un libro, y como es un científico y trabaja en una de las áreas más difíciles de la astrofísica, entonces le hemos dado un libro en español, pero difícil. Le íbamos a dar un libro fácil, un libro de García Márquez. Do you know García Márquez?
Claro,
Of
claro,
course.
claro, claro.
And do you know Julio Cortázar?
No.
Oh, you will know it.
Yeah?
Oh my God, you will know him. It's great. It's great. So,
See?
yes.
Is he right?
Please ask your wife. Okay, this book is not for your wife. Maybe for your daughters.
Okay, very good.
They speak in Spanish.
Also, yeah.
Okay. So all of us
Qué bonito.
are signed. Okay. So this is a present for Colombia, from Colombia.
Thank you very much.
So thank you. Okay, and
there was something else.
okay, this is para las cervezas belgas.
Eso.
Para que pongan los vasos de cervezas belgas en la casa.
Justo caben, creo.
Exacto.
Bueno, muy bonito.
Now,
Muchas gracias.
what about the picture? Have you taken the picture, Rafael? We need to take the picture with the bravest of the braves. ¿La tomó aquí o qué? A ver. con cara de lente gravitacional caliente.